Intermolecular forces are the forces in between molecules. In particular, we're talking about the attractive forces. The attractive forces between molecules is really what ends up governing all physical properties. And when I say physical properties, I mean boiling point, melting point, viscosity, surface tension, stuff like that are physical properties. And it's really governed by how strongly these molecules are stuck together. Turns out a lot of these intermolecular forces also affect the way chemicals react, because a lot of these same forces govern the way chemicals come together, and then if you can get them together, you have the possibility of a chemical reaction. We generally cover three basic intermolecular forces that we give three distinct names. The differences are really pretty subtle. It all comes down to the difference of a positive charge and a negative charge. That's really what the attractive force is about. So you have positive and you have negative. The more positive it is, the more negative it is, the stronger the force. This is simply Coulombic attraction. Positive attracts negative. And we have all degrees of this. It's just a matter of how positive and how negative. Most molecules, being neutral species, do not have full positives and full negatives on them. That tends to be the world of ionic molecules. So we're constantly writing partial positive and partial negative. We even have the way we symbolize it on paper, which you should be used to as these partial positive and partial negative charges. Matter of fact, if you can get enough distribution within your molecule to where you have a lot of positive charge on one side and negative charge on the other, you can get what we call a polar molecule. A permanent dipole is a polar molecule. And if you have a permanent dipole, you're going to have a setup within the molecule where you always have partial positive, you always have partial negative. And those are going to get together. That's called dipole-dipole interaction, and that is the strongest interaction you can have within a molecule to another molecule. Now we have a subset of that that's actually the strongest version of that. They're even stronger than a regular dipole-dipole. And we call it hydrogen bonding. And it's really because it involves hydrogen being the partial positive part of this molecule. Anytime hydrogen is covalently bound to a very electronegative element, and I'll be specific here, it has to be bound to fluorine, oxygen, or nitrogen. And when it is, it becomes so partial positive, and the oxygen or nitrogen or fluorine becomes so partial negative that you get an even higher amount of attraction. So we go ahead and classify that in its own class. We call it hydrogen bonding, but it's really just dipole-dipole interaction, just up a notch. At the low end of the scale are nonpolar molecules. Now, nonpolar molecules are molecules that have no dipole moment whatsoever. They usually are nonpolar due to symmetry arguments, meaning that whatever you argue pointing one way, there's the opposite way covered somewhere else on the molecule. So all the symmetry wipes out the polarity of the molecule. Good example of this is carbon tetrachloride. Carbon tetrachloride has 4 very polar carbon-chlorine bonds, but they all nullify each other as far as distribution of charge. So it's a nonpolar molecule. However, it will attract another carbon tetrachloride molecule. They do stick. It is a liquid. So there's definitely forces there. So what are they? They're dispersion forces, and they are based on what we say are temporary dipole moments. Temporary dipole moments is when the electrons within the whole molecule are in such flux that at any one point in time, you're going to catch it with a slight positive end and a slight negative. And another molecule is going to get caught in that same time, and there's going to be an attraction there. This will change over time and time again in very fast time frame, yet the attraction is there. So it's a very slight attraction. It's not nearly as strong as a permanent dipole, but that's what we call dispersion forces. So that's all 3 forces together there. We've got hydrogen bonding up at the top, right under it, dipole-dipole interaction, and a little bit below that, we've got dispersion forces. Those are the three major intermolecular forces at play with all molecular substances. We can go into details on each one. That's another story. So right now, just keep straight what the three types are so that when we talk about them, you'll at least know what we're talking about.